So far we've been talking about area between curves, and we know how to find the area under a curve. But let's take this ordinary looking rectangle, and with this ordinary rectangle, let's give it some dimensions. Let's say with this rectangle has a height of 2, and the units can be anything you want, and it has a length of 5. And let's say we were to come along and take this rectangle and rotate it around an axis. And let's say that axis was at the bottom of the rectangle. So if we were to take this rectangle and spin it around this axis, think about what shape we would create. Well, we would create a cylinder. And so with this cylinder, if we think about the volume of a cylinder, the volume of a cylinder is pi times r squared times h. Well, this cylinder, if it's kind of like a can on its side is what it would look like, but this cylinder would have a volume equal to pi. Now, the radius would be kind of like the width, because that's what's going to rotate around each time. So 2 squared. And then the cylinder would have a height of 5. So we find out that the volume of this cylinder, which started from a rectangle, rotated around an axis, the volume turns out to be 20 pi. But what if we were to take this ordinary rectangle, and we'll kind of draw it again, and we'll give it the same dimensions, and we'll say it's 5 and 2. But what if this time we were to change the axis, yes, that's right, and take this rectangle and rotate it over the left side of the rectangle. So we're going to create a cylinder, but this time our cylinder is going to be, well, it's almost going to be like a can of tuna, I guess you could say. It's going to be kind of squatty, but it's going to be kind of wide. So if we do volume for this, it's going to have a volume equal to pi. Now its radius, if you imagine this rectangle coming at you and coming around the red line, it's going to have a radius of 5. So we're going to square that and take it times the height of 2. So the volume of that cylinder created would be 50 pi. So we can take the same two-dimensional shape, rotate it over a different axis, and get a completely different volume and completely different sized solid. And this is an introduction to volume. And what we're doing is we're finding the volume of one of these things. It's called a solid of revolution. Now, solid of revolution is defined as this. It's a solid obtained by rotating a region about what's known as an axis of revolution. Which is another new term. So, solid of revolution. It's a solid obtained by rotating a region about an axis of revolution. Now, an axis of revolution could be something that's horizontal, like the x-axis. It could be something that's vertical like the y-axis, but it could be anything. Now, we're not going to get into rotating anything on a diagonal, but we are going to look at writing volume formulas for things rotated about a horizontal or vertical axis. Methods we're going to use to find volume is the disk method. And imagine taking a circle that has an area of pi r squared. And what if we gave that circle a little bit of width and made it into just a really, really thin disk? So that width we could call h, pi r squared h. So imagine all these disks are stacked on top of each other. Now, all of these disks are put together, and let's say we have this this curve, and we want to find the volume of this shape right here revolved about the x-axis. Well, imagine that this function up top here would actually be towards the bottom as well, so I'll kind of draw it here also. So we're creating a figure that looks like this, and so imagine just a bunch of disks stacked on top of each other. And the width of each disk is oh so very small. If we added up all the volumes of each of these disks, we would end up with the volume of the solid of revolution. And so it's kind of like the exhaustion method, but from a 3D standpoint. So here's a formula we're going to use for the disk method. We're going to use this. The disk method is then pi times the integral from a to b of some function, we're going to call it r of x, all squared with respect to x. Now, a and b are going to be the boundaries that we use. And r of x is going to be the function. Now, what each part of this formula means is, if we go back to our cylinder, pi r squared h, there's the pi. The radius of each disk is going to be the function squared. And the width of each disk is the dx, that's the h. That's pi r squared times h. Each disk has a different radius depending on the function. And so each disk is solid right now. There's no holes in it. That will come later. The goal in this is to be able to write a formula to find the volume of the solid of revolution bounded by and revolved around a certain axis. And that's where we're going to head in this particular concept.